Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, the Quark Group has Dmitry Maslov visiting. So we're excited to have Dmitry here. Dmitry received his degree in mathematics from Moscow State University in Russia in 2000 and received his master's and PhDs in computer science from the University of New Brunswick, Canada in 2002 and 2003. Currently, Dmitry is working as the program director in the Division of Computing and Communication Foundations, a Directorate for Computer and Information Science and Engineering at NSF, and is also an adjunct faculty member at University of Waterloo in the Department of Physics and Astronomy, and also for the Institute for Quantum Computing, which is there. His research interests include quantum circuits and architectures, quantum algorithms, quantum information processing, logic synthesis, reversible logic, and circuit complexity. And today we'll hear about synthesis for reversible circuits with applications to quantum circuits. So we're excited to have Dmitry. Let's welcome Dmitry.
Thank you for the introduction. So I right away found an error. It's on the title. I forgot to change it. So hopefully for the rest of the talk there will be no other corrections. Okay, so what I would like to talk about today is about different kinds of optimal searches for the implementations of different kinds of functions. So we'll talk about optimal synthesis of reversible circuits, optimal synthesis of multiple qubit unitaries, the truly quantum circuits, in other words, and optimal synthesis of single qubit unitaries. So the optimal synthesis of single qubit unitaries is actually highly relevant to the work done by Alex and Krista. So our result we developed independently of Alex and Krista, but it seems as if we developed the same thing from looking at it at two different angles. So, but I'll talk about it and we'll see what the differences are. So a good thing is we just heard Alex's talk, so it will be, it's still fresh in the mind. So hopefully the differences will be evident. I wanted to show those a few gates. The NOT gate, the CNOT gate, the Toffoli gate, and Toffoli with more controls. So for example, so this Toffoli has two controls. It computes Z exclusive or Boolean product of variables x and y. The Toffoli 4, it has three controls. So here it will compute exclusive for of this variable times Boolean product plus Boolean product of the three variables above. When we talk about circuits, the difference between reversible and quantum circuits and the classical circuits is that we do not allow fan-outs and we do not allow feedback. Because the way it works in quantum is, and the reversible case, the circuits aren't physical, but they describe the time evolution. So having a fan-out would correspond to duplicating the particle, and due to energy mass conservation, we probably cannot do it. And the feedback would be travel back in time, which is also a bad idea, probably. I mean, there are closed time-like curves where you can probably travel back in time, but then the complexity implications are such that probably it is still impossible, even if the history of traveling back in time were consistent. Anyways, that is not the point of the talk. So the quantum gates, the Hadamard gate, we already saw it earlier today, is a 2x2 matrix. So I'd like to illustrate how the Hadamard gate works on this two-dimensional picture, which you can also think of as three-dimensional picture. This is a CAD0 state, and perpendicular to it, a cat1 state. So what the H gate does, the Hadamard, it reflects the state about this axis. So algebraically, if we apply H gate to the cat0, which is vector 1, 0, oh, I have a pointer. Okay, so which is vector 1, 0, then the result of the computation is this state. And indeed, on the picture, we can see that if we take this vector and reflect with respect to the to this line, then we have this vector, and this is exactly what h of 0 is. So it's a reflection for 0. For completeness, let's verify it for cat1. So h applied to cat1 algebraically is going to be this expression. And in terms of the picture, we take this vector, we reflect it with respect to this line, and this is the result. And we could see that the result actually corresponds to what we computed algebraically. So this coordinate is 1 over square root of 2, negative 1 over square root of 2. So H gate is a fairly nice and easy to see. So the other gates that I'm going to use in this talk include the T gate. So unlike Alex, I prefer to actually write it down as 1e to the, so this is the 8th root of unity. So the w here corresponds to the 8th root of unity. This is how I will denote it. I will actually use the 8th root of unity throughout the talk. So I'd rather introduce it right away. We already discussed the reasons to use the T gate. Well, we needed because of the fault tolerance and because we can actually physically construct it. So unlike other gates that are not necessarily as obvious how to construct. And as such, they need to be implemented as circuits with what we know how to construct. So the phase gate, you can think of it as T squared. So when you look at the matrix, this matrix squared is the square of its entries. So the only thing that changes is w, which is 8th root of unity. It is changing to the 4th root of unity and becoming I. So the phase gate is 1, 0, 0, I. In practice, we do not implement the phase gate as a sequence of 2 T's, because that would be, I mean, that would be correct, but it will be way too expensive. Because if one were to estimate the relative costs of the T gate with respect to phase gate, then in a good sense, if the T gate was associated with some sort of physical cost, call it 100, then the phase gate would cost about 4. So it is much, much cheaper. So the Z gate, again, we can think of the Z gate as P squared or T to the power of 4. And then when we raise elements of this matrix to the power 4, this is 1, 0, 0, and this becomes negative 1. So again, we don't implement Z as a circuit with 2 P's because there is a direct implementation of Z. And I believe its physical cost is about, compared to T, is about 1 on the scale that I introduced. So T gate costs 100, this costs about 4, this costs about 1. So it's much, much cheaper. So why we consider those gates? Here are a few reasons. So using the library with CNOT gates, we can compute linear reversible functions. So those functions are quite important because, for example, when we talk about Clifford circuits, linear reversible functions due to Aronson and Gottesman is the most difficult part of the Clifford circuits. In fact, the very simulability of the Clifford circuits has the bottleneck of simulating linear reversible circuits. So the efficiency of linear reversible circuits determines the efficiency of Clifford circuits. The Clifford circuits now, we don't technically need the Z gate here, but I included it nevertheless. I mean, Z is just P squared, so we could avoid it completely. This library is overspecified. The Clifford circuits are important because because they're required in the error correction. And in quantum computing, we will likely need to correct the errors, more likely so than in the classical computing. Well, in classical computing, we started by studying the error correcting codes, and then it turned out that for computational purposes, we don't need those. It looks like in quantum, we actually will need those. So, and Clifford circuits are very important. So T plus CNOT, this is an interesting class. This set is actually discrete. It contains a kind of linear reversible circuits modified by T's. This is an interesting set. So Toffoli, you can also add CNOT to the Toffoli, but in a sense, if you have a single qubit residing in state 1, then the CNOT is a Toffoli using this single qubit. So the Toffoli gate gives us any reversible function. When we have the library with H and T gates, Hadamard and T, then we can implement any single qubit gate. And by that I mean approximate, because we have infinitely many unitaries. So with any discrete set of gates will not directly implement, is not enough to implement any unitary from an infinite set. But we can efficiently approximate those. And finally, Clifford+T gives all unitaries via the approximation. Okay, so the first problem I'm going to discuss, contrary to the advertisement in the abstract, it made more sense to me to invert the order of the things I'm going to discuss and start with the reversible circuits, because it is simpler. The problem that we formulated is we want to synthesize optimal circuits, and optimality means minimal resources such as gate count, depth, minimal. So what else we can do? We can do the weighted gate count. We can do weighted depth, restricted architectures. I mean, there are lots of different metrics that one could use. Why do we want to have optimal implementations? Well, one of the reasons it could be a useful library for those physicists trying to establish a certain experiment and having a limited control over their quantum mechanical system. So, for example, if your quantum mechanical, if your apparatus allows you to apply 10 gates, and you look up the unitary or the transformation in the library, and it turns out that the optimal circuit has 12, then no, you cannot implement it. You have to gain more control over quantum mechanical system before you can do something that complex. Perhaps a bigger reason is the peephole optimization methods that are being currently an important part of any reasonably sophisticated compiler. So once you have a library of optimal implementations and you want to optimize a quantum circuit, you just cut small subcircuits, compare those subcircuits to the optimal circuits stored in a library, and see if it is beneficial to do a substitution. A trivial idea, but very practical. And finally, the mathematical curiosity, computing the value of the Shannon's complexity function. In other words, what is the number of gates required to implement a function of a certain size? So in 2002, Shanda, Markov, Hayes, and maybe somebody else, I don't remember all the authors, showed that reversible functions with 3 inputs require no more than 8 gates. So we improved this by looking at the 4-bit reversible functions. We showed that the number of gates required is 15. I do not believe that L of 5 can be computed in my lifetime anyways, even if the scaling continues, even if the Moore's law continues to hold. The problem is too complex. What's that?
Regression,
yeah, right, but can you prove that? You can probably guess, but can you prove it? So A reversible 4-bit function is a permutation of the 4-bit integers. And it may be computed using those reversible gates I introduced, the NOT, CNOT, Toffoli, and Toffoli 4. The reason I need a Toffoli 4, I need, for completeness, I need an odd permutation. And the other permutations are even. So I just need something that is odd. We want to synthesize optimal circuits. And what was done previously in 2003, Igor Markov, in the previous slide I said 2004, but I mean 2002. 2002 was their conference paper. This I'm referring to a journal paper. So they showed optimal reversible circuits for 3-bit reversible functions, and there are 2 to the power of 3 factorial of them. So factorial is applied to 2 to the power of 3. Which is 8 factorial, in other words, 40,320. So in year 2006, again, the Markov's group at the University of Michigan tried to synthesize 4-bit reversible circuits, and they were able to synthesize 26 million of them. The number of reversible circuits, 4-bit reversible circuits, is 2 to the power of 4 factorial, which is 16 factorial. It's a 13-digit number. So this number is an 8-digit number. So there are quite a few more digits to go. We introduced 2 searches. So first, let me explain how to synthesize a given function, and then I will explain how to synthesize all functions. So in a sense, if you can synthesize all functions, you can synthesize any one function, because you run the search until you found the one that you want. But the search is very long, so it's not practical. And conversely, in principle, if you can synthesize any one function, you can synthesize all by waiting long enough. But then again, that also turns out to be non-practical. So we have developed 2 algorithms. So now I'll explain how to synthesize any given function. So we use breadth-first search to find optimal circuits with some L divided by 2 gates. We choose L divided by 2 to be a high enough number to guarantee that our algorithm works. In our particular case, L divided by 2 is 9. And the L divided by 2 has to be greater than the number of gates needed to implement any reversible function of 4 inputs. So once we found all circuits with at most L divided by 2 gates, so any optimal circuit for any function can be found in this big database of the halves of all optimal circuits by searching this database. Of course, in our experiments, it turned out that the number of circuits that we store is this number. So so this is the number of circuits with up to 9 gates. Of course, if you just have this database and you search it twice for 2 halves, the complexity becomes too high. It becomes s to the power 2, and the s is this long number I gave on the previous slide, so it is not efficient. So we need something more efficient. And okay, so this is what it says. If we just search for 2 halves, this is how many Boolean operations we need, and we can do, let's say, 10 to the power of 9 in a second. So this number becomes too large to be practical. So what we do instead is we hash the table of circuits. We use Thomas-Wang hash function for those familiar with hashing functions for permutations. If not, then it's just a hashing function. I don't know why it's efficient, but it is. So with s log s, we have approximately this many Boolean operations. I mean, of course, I'm kind of cheating here. It's not this many operations, but just to show you that this number looks much shorter than this number. So the difference between, yeah.
How hashing? What is the use of hashing?
Oh, okay, all right. So the use of hashing, so you need to find two halves, right? So to find one half, you need the number of operations equal to the size of a database. So, but to find the second half, we use a hash table. So we calculate the hash key, and we query the database if it has any values with this hash. And that is only polylog on the size of the database.
So on the other half, which gates hash helps you to look at?
Okay, so
You're actually computation.
yeah, so
Okay, got it.
oh, you got it.
Yes.
All right. So finally, we actually do one more reduction, which in theory may be not as impressive as it is in practice. We say that if we have an optimal circuit, then it is still optimal with respect to input-output permutation, of which there are 4 factorial. 4 variables, we can permute them in any order. 4 factorial is 24. And function inverse. So if we have an optimal circuit, then the inverse of this circuit is also an optimal circuit. So we can pack almost 24 times 2, being 48 circuits into one circuit, because they're all, in a sense, identical. So here is a recap. So we started with the solution. Basically, we said that we use a breadth first search that requires order of n space and order of n time complexity, where n is the number of, it's 16 factorial, the number of circuits. So we first reduce it to order of roughly, this is a little bit of cheating. This is a lower bound, and by no means an upper bound. We cannot calculate an upper bound, but we believe that the upper bound is actually much lower than the order of n. And what we do is we synthesize only halves of all optimal circuits. So then the runtime reduces to order square root of n, but we have to search for 2 halves, and the complexity of the search is the square of the size of the database. Then we introduce the hash table and reduce the time complexity to square root of n polylog square root of n. This is actually a polylog, but I mean, log, polylog, not a big difference as long as we have square root in front. And a small constant, because it has to be practical. And we reduce, furthermore, the space complexity by a factor of 48. So it turns out that for a random reversible function of 4 variables, it has no symmetries, more often than not. So the actual factor, practical factor, is 47.95, I think. So which is pretty much says that only in 1 in 100 cases there are any symmetries whatsoever. So this is how the distribution of reversible functions requiring a certain number of gates looks like. So the reduced functions is what we actually store in the database. This is the actual functions. So what here this table says is it says that there are 4.8 million different reversible functions requiring 5 gates in an optimal implementation. So we then experimented with 10 million random functions. So on the input we have 10 million random functions fed one by one, and on the output the software produces an optimal implementation. In principle there could be more than one optimal circuit, but as soon as we find one we say, well, there you go, it is optimal. So what is surprising about this search is the time it takes to find an optimal implementation being 0.07 seconds per circuit. It is incredibly fast. I could not almost believe how fast it is, because so if you think of having the answer being all optimal circuits stored on a hard drive without any reductions, then this hard drive would have to be at least 100 terabytes. So if it were a 5400 RPM hard drive, then the expected time to extract data, a single bit of data from such a hard drive, would be 0.01 seconds. So ours is faster, is 0.07 seconds. So it is surprisingly fast. Okay, so now to synthesizing all functions. Well, we could not come up with anything very smart, so what we did is a breadth first search. So what we did is we composed an indexable set of 4-bit permutations while taking input-output relabeling and the inverse symmetries into account as much as possible. So in practice, what we were able to do is we were able to reduce the 16 factorial, the number of all functions, by a factor of approximately 12 to 13, not the full 48. Because with both symmetries included, relabeling and inverse, we could not come up with an easy-to-compute index. And we wanted to have an indexable vector so that we can change it according to the function value, and we could calculate the function according to the index very quickly. So that was the requirement. Then what we did is we ran the depth first search on the bit vector to toggle those bits if the function is implementable with an optimal circuit of a certain size. The bit vector that we used is 209 gigabytes in size. We used a 128 gigabyte machine, so in order to feed that vector into RAM, we needed to break it into 3 parts. So we actually ended up running the calculation on 9 nodes of a cluster, IQC cluster, and the total runtime to calculate all optimal circuits is about 1 million seconds, which amounts to about 13 days. So here is the complete distribution of the number of gates required in optimal implementations of the 4-bit reversible functions. So note that there are only 144 functions of size 15. And interestingly, if you remove the symmetries, there will be only 5. So meaning 1 has no symmetries, and 4 more have 2 symmetries. Okay. So now I'll talk about multi-qubit circuits. So what we do in this project is we try to synthesize optimal implementations for some small useful transformations. So for example, the Toffoli gate. I mean, we probably need the Toffoli gate because it seems to be used everywhere you look at. It is used in Schur's integer factoring algorithm for the reversible computation part. It is used in fault tolerance for the syndrome detection, and it is used, well, it's used everywhere. And there is, of course, an implementation of the Toffoli gate using the library of CNOT, Hadamard, phase, and T. And the reason we use this library of gates is due to the restrictions imposed by error correction. But we wanted to check if this implementation is optimal and find optimal implementations, if we can, for some other small functions. So again, what we do is similarly to the previously described project, we compose a library of depth optimal circuits. So this time we decided to look at depth, but could as well be any other function. So whichever function you want to use, we can use in the software, as long as it doesn't have too many values. So we search the library of halves to find an optimal implementation and output the circuit. So the interesting part here is the results. So for example, the Toffoli gate, speaking of the Toffoli gate, is we were able to find an implementation with the overall depth 8. I believe the one in Nielsen-Chuang book has an overall depth of about maybe 10, 13, 15, 13, 15, somewhere along these lines. Of course, here the T depth, and T is the more complex gate, likely. It is not necessarily the case because, for example, if you consider for example, a Hamiltonian used in liquid state NMR, then the T gate is actually the least expensive of all of these gates in a non-fault tolerant implementation, in a direct implementation. But if you want to do something fault tolerantly, scalably, then T has to be implemented differently. It's a logical gate. So the T depth here is 4. Which sort of improves what the Nielsen-Chuang had, because they had the T depth, I believe it was 7, but via playing a little bit with the circuit could be reduced to 6. So we could reduce from, or what's that? Excuse me?
The T depth, are you sure it's not 5 there?
Yeah, because you can execute this and this in parallel by executing first stage, second, third, fourth, and then this is 5th, okay, and so on. Yeah, so it's 4, but you have to kind of rewrite it a little bit. So then we found this circuit with T depth 3. So this is, it's not written here very well, but this is one layer of T's. This is the second layer of T's, and this is the third layer of T's, which gives the T depth 3. So what we have also done, we compared to our synthesis algorithm to the one we were able to find online, and pretty much the only one available is the Dawson's implementation of the Solovay-Kitaev. A great thing about it, I mean, it leaves lots of room for improvement, but the great thing about it is it actually works with multi-qubit circuits, which is great. So this is the scaling of the Dawson's implementation compared to our implementation. So as you can see, we can go further in depth than the Dawson. But in a way, it's not the best comparison because, for example, if we use Dawson's code with 4 levels of recursion to generate a controlled H gate, we come up with an approximation that is 0.34 distance away from the controlled Hadamard, which takes about 2 minutes, and the implementation has about 1,000 gates, whereas we synthesized an exact circuit. Our exact circuit has 7 gates, and it took 0.5 seconds to synthesize this circuit. But we're not claiming we're like 100 times better because we're not comparing apples to apples here. We're comparing apples to oranges. But we only had oranges to compare to, and we wanted to make a comparison of sorts. Another interesting thing we have tried to do, so here is an optimal implementation of the controlled P. Note that the T depth is 2. However, if you consider the controlled P as an operation of 3 qubits, then this circuit is an optimal circuit implementing the controlled P. Note that the T depth here is actually 1. So we were surprised by this phenomena, and then we were able to prove the following theorem. Basically, what the theorem says is if we have a circuit with CNOT plus T gates, we can parallelize it to any depth you want. But it's subject to how many ancilla you can give me. If you can give me sufficiently many, depth 1 I can do. If you don't give me as much as I want, then maybe depth 2. If you give me only a few, then the depth will be maybe closer to the number of T gates. So this is formally the statement of the lemma, of the theorem. So this number can actually be improved, but I mean, not going to talk about that much. Still, it's interesting that any CNOT plus T circuit can be optimized to depth 1T. So I have to also say that a part of this research and the theorem and some of the follow-up things that we're currently doing was also inspired by discussions with Peter Zeilinger, who showed us a T-depth 1 optimal Toffoli implementation. Well, it's obviously optimal because there cannot be anything better than the T-depth 1, but it uses 4 ancilla. Another thing we tried to do is we took the Clifford gates and we took the T gate and we look at their controlled versions, and it turned out that all the controlled versions can be implemented. In fact, we implemented them using our algorithm, we implemented them optimally. So we then realized that if a unitary U can be implemented exactly over the Clifford+T library, then so can the controlled version of U, the controlled U. If the vector of costs for the unitary U was, well, first coordinate is the number of Hadamards used, second is the number of phase gate used, third is the number of CNOT gate used, and fourth is the number of T gates used. Then to calculate the number of Hadamard phase CNOT and T gates, what you need to do is multiply this column vector, it's actually a column vector, by this matrix. So, yeah.
Give some road path as to how do you get to this theorem?
So what we need to get to this theorem is we took the controlled H, implemented it optimally, and actually if you look at this matrix, you can sort of see what happens. So the controlled H when implemented optimally requires 2 Hadamard gates, 0 phase gates, 2 CNOT gates, and 4 T's. Okay, so probably I read it incorrectly. So let me think for a second. We multiply this matrix by this column vector. So yeah, they're columns. So yeah, so so I had to read the column instead, not the row. So you need 2 Hadamard gates for controlled Hadamard. You need 2 phase gates. You need 1 CNOT and 2 T's, and that gives you a controlled Hadamard. And controlled P is described by this vector. It's funny how controlled P does not require P. It requires only T's and CNOTs. But in a way, T is the square root of P. So it makes total sense because there is a direct relation between a square root of a gate and its controlled version. Yeah, it's on Nielsen-Chuang, page 182. One of my favorite circuits, so I remember it. Okay.
So how do you get to the point where you prove that lambda U can be implemented exactly?
Since U can be implemented exactly, we take the circuit for U and we control every single gate. If we control every single gate, it is equivalent to controlling the whole transformation. And for each controlled gate, we found its optimal implementation. And we substitute the controlled gates with their implementation. Yeah. Okay, so now to the single qubit unitaries, finally. So here is the original motivation for our research and what we actually tried to accomplish before we wrote what we wrote. We wanted to study if a unitary U can be implemented exactly in the Clifford+T basis. So we obviously want an exact implementation, and the reason for that is there are enough errors in quantum algorithms already. So firstly, there are algorithmic errors, such as the Shor's algorithm does not guarantee you the answer with probability 1. It's not Karatsuba's algorithm that always guarantees that you multiply two integers and you actually do get the result. But it's a randomized algorithm in a sense, not a randomized. It's quantum, but you get the answer with a probability. We have errors due to decoherence, and that's the reason why we have the error correction and fault tolerance that increases the circuit sizes when you go from logical circuits to physical circuits by a factor of what must be close to 1,000, if not more than that. In other words, it is expensive to have those decoherence errors. And there are systematic errors in the controlling apparatus, and again, they also need to be fought with. So what we were able to prove is we were able to prove the following theorem. In the single qubit case, the set of all unitaries implementable in the Clifford+T basis is equivalent to the set of unitaries over this ring. So this ring is an integer extension of I and 1 over square root of 2. We furthermore conjecture that in the n-qubit case, the set of all the set of all unitaries on n qubits implementable by circuits in the Clifford+T basis is equivalent to the set of all unitaries over this ring, as long as there is an ancillary qubit available that resides in state 0. So the requirement, I will not be able to prove the conjecture. This is what we tried to do. We couldn't do it. We made some partial progress, but not nearly enough. What I can do is I can illustrate that the ancilla qubit, the requirement to have ancilla qubit is essential. And then I will outline the proof of the theorem. So first, let me show that the requirement to have ancilla in the formulation of the conjecture is important. In particular, I would like to illustrate it with the example of the controlled T gate and the determinant argument. So if you look at the determinant of the controlled T viewed as a matrix on 2 qubits, a 4x4 matrix, then the determinant equals to the W, and to remind, the W is the 8th root of unity. However, the determinant of gates that we can work with, Hadamard, phase, CNOT, and T, belong to the set plus minus I plus minus 1. So since determinant is multiplicative, multiplying these numbers, we can never get the W. So we cannot have the controlled T on the 2 qubits. You could say that, well, what if we want to build the controlled T up to a global phase? Well, a little bit more hand-waving, well, maybe not necessarily hand-waving, but formal arguments actually shows that no, you cannot do it up to global phase either. So, yeah. No, you cannot. It's basically the same determinant argument, but have to spend a bit more time. Nevertheless, controlled T may be implemented using 3 qubits by this circuit. This is unnecessarily complex. Essentially, what this circuit does, it applies Kitaev's trick. If I have a pen and a paper, I'll show a much simpler circuit. So we want to implement a controlled T. So what we do is we do controlled swap. This qubit resides in state 0. We do a controlled swap. Then we apply T here. And we apply Fredkin again. Okay, so Kitaev's trick from 95. My other most favorite circuit, I guess. So here it's just optimized a little bit. In fact, it actually optimized even though it doesn't look like such.
So all this kind of complexity goes into controlled swap, is that?
Yes.
It's all symmetric except for the one extra
Yes.
T.
Yeah. Exactly.
There's one extra T dagger. No, all the way down at the bottom left, there's one extra T dagger that would have been a T on the right, which would have given you the same thing back. And so that was your T that you have on the other one for the control swap.
Uh-huh.
Everything else, if you look at it, are just
Yeah, it is
inverses all the
symmetric.
way out.
So yeah, so this is kind of inverse of this.
Exact, except for one gate.
Or a complex conjugate, if you
Right,
want.
right.
Because complex conjugate of CNOT is
Oh,
just
yes,
the
there it is.
CNOT.
Yep.
Complex conjugate of T is T complex conjugate, and of P is P complex conjugate. And H, the complex conjugate is H.
Yep.
Yeah. Yeah, so it is symmetric, just like this circuit. The parent is also symmetric with respect to T. Okay, so now to the proof of the theorem. To remind you, what we're trying to prove is that the set of all unitaries over the ring of the integer extension of I and 1 over square root of 2 is equivalent to the circuits computable by H and T gates, because Clifford becomes pretty much H and P, but P can be simulated with two T's, so H and T suffices. So firstly, from a linear algebra book, we know that it's actually, I'm cheating here a little bit. In linear algebra, this is e to the I phi for any phi, but we know that any unitary can be written in this form. So k runs from 0 to 7. So you can, if you look at those unitaries of this form for different values of k, then they are all equivalent up to multiplication by powers of t. So in a sense, when you have a 2 by 2 unitary, what you have instead is just the vector xy, because everything else, the column vector xy, because everything else you can restore if you can get to the vector xy. So this observation helps us to move from the synthesis of unitaries to the synthesis of states. If we can synthesize states efficiently, if we can synthesize any state over the ring, then we can synthesize any unitary, because unitaries can be easily restored. So to show that we can synthesize the states, we use the notion of the smallest denominator exponent. The smallest denominator exponent, here it is defined formally, but it is an analog of an irreducible fraction for rational numbers. So when we look at the ring that is an integer extension of I and 1 over square root of 2, we know that we have some fractions where the denominator is a power of the square root of 2. So SDE is just the power of the square root of 2, defined such that it is what we're looking at is an irreducible fraction. So first, a lemma, it's actually very simple to prove. If you look at a 2 by 2 matrix, then SDEs of all elements of this matrix are equal. So the reason for that is if this number has denominator square root of 2 to the power n, and this one has square root of 2 to the power, say, n plus 1, then this vector has to be normalized, and the normalization doesn't work out. It's irrational. It's like proving that the square root of 2 is a rational number. Pretty much the same argument. Very easy. Okay, so next thing we do is we consider the result of multiplication of a vector, and now we work with vectors only because we know that they're equivalent to matrices, by h multiplied by t to the power of k. So by multiplying 1, 2 matrices by a vector column, we get this result. So now I'm going to cheat a little bit in the sense that I'm going to show two technical results that I'm not going to prove, but I'm going to claim that it is proved in the paper. I just don't want to prove it. The proof is not very difficult. It's just technical. You have to study the properties of SDE for a long time before you can prove this inequality and this equality. So let me describe what the inequalities are and what is the meaning behind them. So So we want to show that by multiplying a state, by applying h t to the power of k to a state, we change the denominator by no more than 1 in either way. We can increase it by 1, we may not change it, or we may decrease it by 1. This is what this inequality states. It states that SDE of the square of this value, and this value can be found here, minus SDE of this value, which is this value. So the first coordinate of the vector we're looking at, it is squeezed between 1 and -1. So it can increase by 1, decrease by 1, or not change.
Is it the case the denominator will not change sometimes?
Yes. Yeah. 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 So, and a second very interesting thing that we need to prove, that we actually do prove, is for any s in the set -1, 0, 1, we can find a k such that the difference of those SDs, so this expression is exactly the same expression as this expression, equals to exactly s. What this means is by applying h t to the power of k, we can reduce the denominator by 1, well, power of the denominator by 1. We can not change it, or we can increase by 1. So at this point, you probably are thinking, well, there you go. We have an algorithm for the synthesis. So we always find s such that the denominator, or we always find k such that the denominator is increased by 1. And then when the denominator is the power of the denominator is small enough, then we can use breadth-first search to breadth-first search all those unitaries with small denominator size. And this is exactly what we do. So here is the algorithm. On the input, we have column vector. Okay, think about it. On the input, technically on the input we have a matrix, a 2x2 matrix, but we right away drop the second column of the matrix, and we only look at the first column. So we do restore the second column at the very end, but I already said too many things about a very trivial thing. So the output is the circuit that prepares state xy from ket 0. So the way the algorithm works is, while SDE of the first component of the column vector we have is greater or equal than 4, we find k such that application of h t to the power of k reduces the denominator of x. And we substitute h t to the power of k multiplied by vector column xy into xy. So this, the denominator of the first component of this vector, is smaller than the denominator of, and is smaller exactly by 1 than the denominator of this one. So in a sense, for the SDE of the square of the first component of the vector greater or equal than 4, the set of Clifford+T circuits on a single qubit is sort of flat. And at every level, you can predict what is happening. You can increase the denominator, you can decrease it, it may not change. So it's very predictable. The behavior is very predictable. And we brute force finally when we cannot apply this step anymore because SDE is less than 4. We basically brute force all the implementations of all unitaries such that SDE is less than 4. There are probably close to 20,000 of those, but a few in either case. Yeah, so they can be easily brute forced and stored. So let me prove H optimality. In other words, let me prove that the number of Hadamard gates is actually optimal in our circuits. So to increase or decrease SD by 1, we need precisely 1 Hadamard gate. It is proved. So the set of all unitaries with SD of x squared equals 8 equals to the set of H optimal circuits with 7 Hadamard gates. We ran a computer search to actually verify that this statement is correct. So this statement is verified by a computer search. As such, we conclude that This is our n equals 1 a sort of state in the mathematical induction. This is the induction step. So we use the inductive proof to show that the number of Hadamard gates required to implement a particular unitary equals to the size of the denominator of x squared, where x is the top entry, u11, plus 1. That's the number of Hadamard gates. And apparently, our algorithm just matches SD of x squared plus 1. So we furthermore looked at possible T optimality. We cannot prove T optimality, but we can. What we can do is we can, using breadth-first search, we can synthesize all optimal circuits with up to 13 gates, then resynthesize them using our algorithm, and it turned out that we got all the T counts correctly. So we do believe that our T counts are also optimal. We cannot say anything about the P count. So the phase gates, the number of phase gates we use may be suboptimal. We just don't know. We don't have a feeling. We didn't try to study that. But H optimality we can prove is there. The T optimality seems to be the case.
So now, do you define T count as essentially the T count of T to the power k being either 0 or 1?
The T count of T to the power of k equals 1 if k is odd, and 0 if T is even. Because T to the third is PT.
Right.
Yeah. Phase times T. Yeah. So we do this reduction. Yeah. It's just it's for the proof. It's easier to operate with powers of T than to operate with P times T or Z times T or Z times P times T, or because it is much cleaner. So another thing, I didn't have the time to add this slide, but our algorithm, the complexity of our algorithm is linear in the number of gates in the circuit. So what this means that this algorithm, among all algorithms, among all synthesis algorithms, is asymptotically optimal. I mean, just the mere time it takes to write the circuit with n gates is at least order of n, and order of n is the complexity of our synthesis algorithm. So it is efficient.
The depth of the circuit is not an input parameter. You are probably to say
No,
that it's linear in SDE.
Yeah, our input is the unitary.
Right.
So once we have the unitary, we can synthesize. So in fact, what we do in experiments, and I believe this is one of the next slides. Yeah, so let me get to it. It's probably one after that. So here is a similar comparison to Dawson-Nielsen. So it's a software to software comparison. In a way, again, we're comparing apples to oranges. So this is the behavior of the Dawson's implementation of the Solovay-Kitaev. So this is 0 iterations, 1 iteration, 2 iterations, 3, 4, 5, 6, 7. So you could see that the error did not improve here. So the scales are logarithmic. And sorry about the small font size, but it was generated by an automatic software and did not increase the font size yet. So this is the result of using double data format in C++. It does not have enough precision to go beyond errors on the order of 10 to the minus 8 or 10 to the minus 9. It just flats out there. It doesn't work. We, however, used a multi-precision arithmetic, so we were able to go far beyond. Actually, I'll show you on the next slide that actually much far than could be shown in this picture. The smallest errors that we have circuits for are on the order of 10 to the minus 50. And 10 to the minus 50 is likely unpractical. And unpractical in the sense that why would you need something that is this precise?
So the objects being approximated are just the RZs, the small rotations?
Yeah, we approximate these rotations, these 4 rotations. For other things we tried, the graphs look very similar. So we just show the few that look nice, and everything else looks about the same. I mean, it's logarithmic scale, so even if something is different by 30 to 40%, which seems to be the case for a random unitary, right, that this point is going to be maybe here. Yeah, so they're about kind of the same. So this actually very nicely defines the range of points. That's where they're going to land, all of them, for a random unitary. But again, I mean, our database was larger, because you can see for 0 iterations we're better, and our implementation was more efficient. So that's why partially this slope is much better than this slope. Also, another experiment we did is we took the circuits synthesized by Dawson's implementation of the Solovay-Kitaev, computed the unitary, and synthesized the unitary using our algorithm. So the reduction in the number of gates was only on the order of about 50%. So the approximations are not efficient, but their circuits are actually fairly good. Well, 50% away from what we believe should be fairly close to optimal in whatever metric of optimal that you choose. Yeah, but this graph shows that finding a good approximation to a unitary is a much more difficult task than if you have a good approximation already, finding a circuit for it. Finding a circuit is easy. It can be done in time linear in the number of gates in the optimal circuit. I mean, it cannot be better than that. But finding an efficient approximation is very hard. Okay, so here is an example of the experimental results. So here it shows the error down to 10 to the minus 15. So if I click here, we actually have more circuits. Okay, so here are the implementations of the RZ2 divided by the power of n for n between 4 and 30. So each of them approximates down to 10 to the power of minus 50 approximately. So if you want to have a circuit with that approximates to a very small error, then you have to pay a heavy price on, for example, the number of t's, 1.7 million. So actually, we also have circuit files here. So if you click here, it's a fairly small circuit. The number of gates in this circuit is only 73, counting all gates, 28 T gates. So this is the circuit. Okay, not displayed very well. So let me switch the browser then. Okay, so here is the same page. So this is the circuit. You can actually view this circuit using the software for viewing the circuits that we also have on the group web page. It's called the QC Viewer. You can download, play with it if you want to. It's not the best for displaying circuits with millions of gates on a single qubit, but if you have circuits with tens of gates on a few qubits, then it's kind of much nicer. In fact, all of the circuits that I showed today were generated automatically by this QC Viewer software. Yeah. Okay, so let me go back to the presentation. What's left of it? Acknowledgements. So I'd like to acknowledge the help from my students, Matt Amy, who is a master's student, Vadim Klushnikov, who is a PhD student, Oleg Golubitsky, one of the co-authors. He's an ACM programming contest champion, and he's a really extremely good coder, which explains why the numbers in the reversible logic synthesis are so low. Because he has helped tremendously coding it, and he's great. Then Professor Mike Mosca, who is handling the quantum circuits research group in my absence at the University of Waterloo, and NSF, Independent Research and Development Program, that allows me to do research, despite being an administrator. Okay, thank you.
I'd like to know a little more about the high precision arithmetic package you used to
I
get
see.
those big denominators.
Yeah, sure. I can just send you the link to where you can download it from,
So
if
it's-
that's what you want to know.
No, I just wondered what its attributes are. Is it something you implemented yourself?
No. We downloaded it from online. Yeah, it's just available. It's a C++ library for dealing with large numbers,
Yeah,
and it's just that.
okay.
It's one of those
It's a big
libraries.
library.
You don't have to use that library because there are so many different ones.
There's nothing.
Yeah, I even wrote one myself, but it's so
Yeah.
not good that it's not available anywhere. Yeah.
Actually, Bert and Jason has one now.
I know, I helped with it.
Yep, I thought.
Uh-huh. Oh, okay. Yeah, I can't recall where we downloaded it from. Maybe it's yours.
No.
No, this is internal.
Oh, it's internal.
If it
Oh,
were-
may still be yours.
If it were ours, we would leak, yeah.
Yeah, I don't remember which one it is.
There's a thing called GMP from the open source, the GNU world.
Uh-huh.
That's fairly popular. And there's-
I think that's the one we used.
It's
Yeah.
pretty popular.
Yeah, I think that's the one we used. Yeah. Now it kind of pop back and yeah.
Do you have any thoughts on how to prove T optimality for this?
No, we didn't try to prove. We didn't want to step on someone else's turf. Yeah.
But it seems like, when we compared circuits,
I think we can
before
actually.
we have a few more our Clifford
Uh-huh.
has a little more chaff, I think, and but the T's are the same, so it seems
Yes.
that there might
Yeah.
be maybe some modification to the canonical form that would
There may be one. Yeah.
minimal.
Yeah, you see, we concentrated on the Hadamard because that's how we looked at the matrices. We looked at the denominator, and denominator is defined by Hadamard. And between two Hadamards, you can only squeeze one T, no more than one T. So, yeah, whatever that gives.
It's amazing how much algebraic structure there is in all this, of course. But it should
In
surprise
the
us, too.
single qubit case, which in my opinion is super trivial, but the two qubit case, we tried to prove the theorem that we had
Yeah.
in the two qubit case. It's much more difficult. For example, because you need an ancilla that you don't need in the single qubit case. For what it's worth, you have entanglement, which may come into play, and it could only complicate things.
Yeah, so you're looking at some sort of projection or some sort of homomorphic image of the algebra of the 3 qubit case.
I think it's much more difficult. It's
Yeah.
just it's single qubit case is trivial. 2 qubit case is very difficult in my opinion. I mean, we couldn't do much. We were, however, if you would like to know, we were able to prove that the unitary synthesis in the n qubit case can be reduced to state synthesis. We could do that step, but that's as far as we went. And the proof is far from trivial.
But that says unitary synthesis and state synthesis are really equivalent sometimes.
Yeah, in a way they're equivalent, but state synthesis is simpler. Because all you need is any matrix with the column that you want to have. But when you have a matrix, you need the matrix, that matrix. Yeah. So in a way, we reduced the problem of size 4 to the power of n to the problem of size 2 to the power of n, but that wasn't the most difficult part. We don't believe that part is difficult. We believe that reducing it to solving the problem with 2 to the power of n variables, that is difficult.
So when you experimented with the matrices in single qubit case that
Uh-huh.
are exactly representable,
Yes.
right?
No, yeah, we did both. I mean, we used Solovay Kitaev that we implemented ourselves. So when you have a unitary that is not a unitary over the ring that we have, we know, and if it's a 2x2 unitary, we know that provably we cannot implement this unitary exactly. We need to approximate it. For approximation, we use Solovay-Kitaev. It's just that the code that we use is the code that we wrote for Solovay-Kitaev, but not the docent's code, because when we looked at it, we found that we could write something better, so we wrote something better, which we believe is better. And then if we're given a unitary, we first look at it and say, is it the unitary of our ring? If it is, synthesize it using the algorithm. If it's not, use our Solovay-Kitaev to come up with the approximation unitary. It comes up with a circuit, but we don't care about the circuit. We only care about the unitary. And then we use the unitary to synthesize the circuit. So in a way, yeah, so T-approx is the time it takes to approximate a unitary. So because this unitary is not a unitary in the ring. Right. This unitary lies outside the ring. So T-approx is the time spent by our implementation of Solovay-Kitaev, and T-decomposition is the time spent to actually synthesize the circuit using our algorithm. So the software consists of two parts.
I'm curious about this. When you have a unitary over your ring,
yes,
and SDEs are rather large,
yep,
then the things in numerators, the integers, could be also quite large.
yes.
Did you ever have to use a controlled precision integer arithmetic?
We use our own implementation. It's symbolic. It's fully symbolic.
I see.
Because you see, for example, here we have 15,000 Hadamard gates. 15,000 Hadamard gates implies square root of 2 to the power 15,292 plus minus 1, approximately. Yeah, so we needed our own arithmetic for that. So we used our own arithmetic.
So you essentially have an algebraic package that deals with Z extended by those roots.
Yeah, exactly.
Yeah, you represent everything by a 3 vector, right? The linear part,
Yes.
the root
Yeah,
part,
exactly.
and the I part.
All right.
Yeah.
All right. Yeah.
So it's, or it's the Gaussian integers extended by square root of 2.
It's actually we represent by 4, but
You could use 4, yeah.
yeah, we use 4.
Yeah.
So it seems like if you had a software that does Z extended by 1 over square root of 4, then dealing with infinite precision integer arithmetic, infinite length integer arithmetic would be a subset of what your package does.
No, because it's very specialized. It doesn't do any of the multiplication.
I'm wrong.
Yeah.
Withdrawn.
Okay. All right. It's suited only for our needs. It has only a limited capability. Very limited.
Any other questions?
Yeah, sure. Thank you.